Well, if you think of this as a trailer to a movie, we've already introduced the latest new Hollywood epic. It's called Sequence of Events Following Vascular Injury. And just like we talked about acute inflammation as being a linear temporal sequence of events, or healing as an orderly array of things that happen one after another, we can also define vascular injury as triggering off a sequence of events, starting out with arteriolar vasoconstriction, and then once that ECM or extracellular matrix has direct contact with the platelets, why? Because the endothelium is gone or damaged, we have the beginning of primary hemostasis, or the platelet plug. And then ultimately we have what we normally think of as the whole coagulation cascade, or the entering in of all the chemical factors from both the intrinsic as well as the extrinsic side of the equation, and the ultimate formation of the fibrin plug, which can then become firmer by polymerizing or dissolving. Let's talk about the major players in this big new Hollywood epic. They're called endothelial cells, platelets, and the massive coagulation cascade. And I would be astounded if you haven't seen the various diagrams for coagulation, so you know I'm going to give you another one, don't you? Let's talk about endothelium. I always described endothelium as being classically like Dr. Jekyll and Mr. Hyde. Endothelium is the most powerful, friendly, nice guy as long as you don't mess with him. It will do everything in the world to prevent clotting. How? Well, it has a variety of antiplatelet properties. It has a variety of anticoagulant properties. And if there's fibrin around, it also has a variety of fibrinolytic properties. In injury, however, once you mess with Dr. Jekyll, it becomes Mr. Hyde, and it'll do almost everything the opposite of what it does normally. And this is under the title of procoagulant properties. There's our friend endothelial cell, and as you know quickly, if you look at a regular H&E or an EM and you see a blood cell, you know that the next cytoplasmic mass after it has to be the cytoplasm of an endothelial cell. And if there's a nucleus next to it, like here, then you know that's a nucleus of an endothelial cell. Endothelial cells are thin, and we normally don't think much about them, but they do so much. And here's what Dr. Jekyll does. Well, he has antiplatelet properties by virtue of the physical anatomic barrier it provides between the platelets and the ECM. Once that barrier is breached, and that's called hemorrhage, we then have the beginning of a lot of things which trigger off the primary coagulation. Endothelium also degrades ADP, so on the virtue of that, ADP is produced by platelets, so if it degrades it, it inhibits platelet aggregation. Endothelium has anticoagulant properties. It makes heparin-like molecules. You know, heparin is one of the most powerful anticoagulants we have. It also makes a compound called thrombomodulin, which is very crucial in the production of the body's most powerful natural anticoagulant called protein C. And if you remember, that tissue factor is the direct process of starting coagulation. It makes a tissue factor inhibitor as well. Last but not least, it also makes a TPA, tissue plasminogen activator, which is a fibrinolytic compound which dissolves or breaks down fibrin. So these are all three solidly good reasons why endothelium is the most powerful inhibitor of coagulation. It has to be, because you know, you got blood on one side of it and ECM on the other, and if it didn't provide that little barrier, it wouldn't be worth anything. When endothelium is messed with, when it's disrupted physically or chemically or by some things we'll talk about, it has prothrombotic properties. One of those is to make von Willebrand's factor, which binds platelets to collagen. So that's already the beginning of your platelet plug, isn't it? It also makes tissue factor, which is the direct compound with besides platelets making tissue factor, endothelium does it well. So we're talking about the beginning of coagulation now, aren't we? The whole direct scheme of the coagulation cascade. In addition, it makes plasminogen inhibitors. So it will inhibit the things that want to dissolve fibrin. So that makes it prothrombotic in itself, doesn't it? What activates endothelium? Well, a lot of infectious agents do. If you remember Virchow's triangle, or if you don't remember it, we'll get to it. It's perhaps can even be the dynamics of the flow can activate endothelium as well, like significant stasis or eddies or turbulence. You know, one of the big triangles of Virchow's, one of the big corners of Virchow's triangle, there are a whole bunch of factors in plasma which can activate endothelium as well. Let's talk about our second big player, platelets. Platelets have alpha granules, and they have the denser delta granules, D for delta, for dense. Alpha granules contain fibrinogen, fibronectin, factor 5, factor 8, platelet factor 4, and transforming growth factor beta. Delta granules, which are the denser things, which we'll see, are bigger and denser and darker, have ADP/ATP, calcium, histamine, serotonin, and epinephrine. And these are all the primary things which are released when platelets do their thing called degranulation. And remember, platelets also make tissue factor as well as endothelium does. Here's an EM of a platelet. You could have guessed that those big, dark, dense granules are delta. The smaller ones, which are pinpoint, are alpha, aren't they? And here's some more platelets. No nucleus, but a lot of dense granules with all the things in them that they're supposed to have in them. And in the process of degranulating, I actually had a movie here, and I don't know if I want to try to show you that movie, but I think I'll take the chance anyway and try to show you the movie of a platelet degranulating, and I hope it works. Yeah, maybe you can see part of it. You can see a dark granule here that is ultimately being released, and as you might guess, that's how it degranulates. Let's talk about the phases of primary coagulation, which we called the platelet plug formation. Well, first of all, platelets have to adhere to the ECM, don't they? Then they have to secrete or release the contents of their granules, or another name is activation. A better name is degranulation. And thirdly, they have to aggregate to form the big platelet plug. And that is what we call primary coagulation. And these are the three linear things that platelets do. I hope you remember it has to have adhesion before secretion and secretion before aggregation. Once you have platelet adhesion, the adherence is primarily to the subendothelial ECM. Remember, we said that von Willebrand's factor is a chemical which, with other factors, provides the bridge between the surface of the platelet and the receptors to the ECM. Remember, the second phase of platelet purpose is the secretion of the contents of their alpha and delta granules. Ultimately, chemically, the binding of antagonists to the platelet surface receptors and intracellular protein phosphorylation takes place in platelet secretion. Last but not least, in platelet aggregation, here are the compounds that are involved. ADP, thromboxane A2, as well as thrombin from the coagulation cascade, which then is the main factor for the production of fibrin. And of course, once you have fibrin now, you not only have the primary coagulation, but you have secondary coagulation as well. So let's take a break here, and we'll start out with PowerPoint number 56. which means we'll be halfway through this chapter. Thank you very much.